Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Dave Whitehead. Welcome to Schweitzer Drive. Power systems move enormous amounts of energy every single second, quietly and reliably. But when something goes wrong, there needs to be something that isolates and clears that part of the power system. That job belongs to the circuit breaker. In this episode, I'm joined by Kylan Robinson, Engineering Director at SEL, and we're going to take a close look at these essential pieces of power system equipment. We'll explore how circuit breakers connect and disconnect apparatus such as transformers, generators, distribution lines, and transmission lines, and how they work with protective relay devices to keep the grid safe. Hi, Kylan. Thanks for taking some time to talk with me. I'm really excited to talk about circuit breakers. But before we get there, why don't you tell me how you got interested in electric power?
Yeah, well, thanks, Dave. I was a student at WSU.
Go Cougs.
Go Cougs, yeah. Simply looking for a summer job and found an internship at SEL. So I really knew nothing about electric power when I joined the company. I was just a firmware engineering intern, but as soon as I got here, I started learning so much, and just the critical nature of electric power as the most critical of critical infrastructure struck me really early on, and fell in love with it.
Let's start at the beginning. What is a circuit breaker, and are they similar to the ones I have in my house?
Yeah, in a sense. Yeah, circuit breakers are devices located throughout the power system on electrical circuits, and they provide protection from undesirable and dangerous situations. A couple of those include overload or overcurrent situations, where the circuit's consuming more power than it was designed to.
So let me stop you right there. Is it the circuit breaker that's doing those functions? Or is it the protective relay or some other protective device that's sensing how much current is actually there and then sending perhaps a signal out to the circuit breaker to open or close?
Yeah, it can be a little bit of both. And
okay.
Actually, we have kind of layers of security and protection in our system, so it's very robust. So like an overcurrent situation would be when I try to run my toaster and my microwave at the same time, right? That circuit is now drawing too much power, and then the circuit breaker opens up to keep me protected.
So that's similar to what happens to the circuit breakers in my house, right? My kids will plug in everything, and then all of a sudden the lights go out in the living room, and I have to walk out to the garage to go figure out which circuit breaker. Now, is that analogous to the ones you might see in a distribution or a transmission substation?
Yeah, the ones that you see in distribution and transmission are just scaled up versions of that. They use a lot of the same technology and a lot of the same principles to operate, but obviously at higher voltages and currents with some extra processing sometimes. That's when you'll see something like an SEL relay added into the system.
Let's go down that hole for just a second. How do circuit breakers work? When a high voltage circuit breaker opens during a fault, what actually is happening inside the breaker in those first few milliseconds?
Yeah, so a lot of breakers have some internal ability to detect, and then they all have an ability to respond to these situations. So a circuit breaker can detect a problem either thermally or magnetically. And so the circuit breakers in your house will have a bimetallic strip in them. And when you have an overcurrent situation, that piece of metal actually heats up and deforms and then flips a switch to open the breaker. That's how that example works. And then there's also a magnetic solution too, where if you have a spike in current, there's a solenoid that detects that instantaneous change in current, and then we'll open the breaker as well. So there's two ways that you get protected there, overcurrent and short circuit.
The circuit breakers you're talking about are in my mind, are more akin to the ones I'd find in my house, or even perhaps like multi-case circuit breakers you might find in, say, an industrial facility or facilities we have around here.
That's
but
right.
A little bit different, or maybe a lot of bit different than the ones we'd see, say, out in a substation yard.
Yeah, correct. So it's the same kind of principles, except when you move to the larger power systems, you're going to use a protective relay like we make at SEL. They have a bunch of sensors out on the power system, current and voltage sensors that are watching values and making the decision on behalf of the breaker. It's essentially a smarter brain for the breaker. We also do a lot with different protection schemes where you can look at measurements from different points on the power system, not just the perspective of that individual breaker. But you can have relays that are working together, sharing analog quantities, making decisions to open and close specific breakers.
Well, we sort of talked about this, but what are the different types of circuit breakers out there, excuse me?
Yeah, so the circuit breakers vary in size, like we talked about. So the miniature circuit breakers in your house, there's what are we call molded case circuit breakers in industrial situations. Those can be kind of in the hundreds of amps range. And then a draw out power circuit breaker when you're talking about thousands of amps, rated continuous current. A lot of the difference in circuit breakers has to do with the technology that they use for managing the arc. Because when you try to open up a circuit breaker, it creates an arc. And the whole point there is you want to extinguish that arc and stop current from flowing down to the loads that are connected to it. So you can have an air circuit breaker where the dielectric, the thing that's between the two contacts, is just air. And then sometimes that's sufficient depending on your applications. Other times you'll want a vacuum where you suck all the air out and the two contacts are touching each other in a vacuum. You pull them apart. There's less material there to ionize and to maintain that arc over time. There's also gas and oil filled breakers as well.
Let's talk about that just for a little bit then. The challenges or the problems with clearing the fault. The circuit breaker in my house really doesn't have a problem, I don't think. There's nothing special about them. It's more like a switch, if you will.
Yep.
Right? But now we start talking about, say, higher voltages or more current. What are the challenges with actually clearing the fault, if you will?
Mm-hmm.
Or what's going on? You mentioned that we open up the contacts on a circuit breaker. There's what depends on what the medium is, but some gas gets ionized and it causes plasma, and it actually acts as a conductor between the two sides of the switch or the circuit breaker, which allows the fault to continue.
That's right. Yeah, and it's actually quite dramatic. When you pull those contacts apart, that arc generates that plasma, and it actually is hotter than the surface of the sun, 20,000 degrees Celsius, right? It's hot enough to melt the contacts, the metal on the contacts, vaporizes that metal, and then that metal becomes part of the plasma as well, the conducting plasma. And so trying to get that thing extinguished to prevent power flow is quite a challenge. And there's a lot of ways to do that.
Then?
Yeah.
What are the ways to clear that fault then, given the plasma physics that are going on?
Mm-hmm. So one of the ways that we do it is in AC systems, we wait for a zero crossing. So alternating current means that the current is sinusoidal and crosses through zero twice per cycle. Those zero crossings are a great opportunity for that arc to be extinguished, and then you pull the contacts far enough apart that the arc does not get reestablished when the current goes up again. So that's the strategy for AC systems. Direct current systems are harder because it's continuous current. You don't have that zero crossing. So you have to find a way to either lengthen and cool and extinguish that arc, or to dump all the energy going through that system to a commutative circuit and then open the contact. So one of the ways that you can do it in an air brake situation is with what we call an arc chute. And so the arc will get formed, and then it'll start to rise because of the heating. And then it can go into this arc chute, which is a bunch of metal blades that start out close together and then start to spread out. So you split the arc into little pieces, and then you spread that arc out. And as it progresses, it gets cooler and then eventually extinguishes.
So really, it sounds like the trick to circuit breakers is how do you manage that arc? If it's an air gap one, it's the distance is your friend there.
Mm-hmm.
But I'm sure at some point the voltages get too high or the current's too much, and that even if you get a zero crossing, there is still an ionized path there that doesn't dissipate quickly, so that you can continue to conduct when it's out of that non-zero part. And then your other ways is to eliminate the mechanism for actually creating the ionized path, if you will, right? Whether it's through gas or other mechanisms.
Uh-huh.
Is that about right?
That's right. There's even air blast circuit breakers where
the puffers,
it'll try to blow out the arc. So
Yep.
It's like blowing out a candle on a much larger scale.
That's cool. In our business, we build protective relays. How do protective relays and circuit breakers work together?
Well, they work hand in hand. That's without circuit breakers, we wouldn't have relays at all. The protective relays that we build really add a lot of intelligence and a lot of perspective to a circuit breaker. So we can watch the power system from the perspective of a relay and tell the breaker to trip before the breaker knows that there's a problem. So it's just that larger context and larger awareness that we have because we are monitoring currents and voltages across the power system. Protective relays also help give you visibility as an operator into the system. Why did this circuit breaker open? Why did it not open? What was the situation leading up to the event? We get all of that from our data logging, monitoring, event reporting, that kind of thing as well.
I was thinking a little bit about, as I was driving in, the evolution of protection and being able to isolate a particular part of the power system that has, I don't know, some damage to it. A tree fell into the line, a line broke, a tower or a pole fell down or whatever. And the circuit breaker allows us to strategically isolate a particular part of a power system and then, close in other parts of it to reroute power to keep lights on to as many people as certainly possible. Dr. Schweitzer's grandfather, E.O. Schweitzer Sr., along with Nicholas Conrad, they both had worked at Commonwealth Edison back in the early 1900s. In about 1911, Ed's grandfather and Nicholas Conrad invented this high voltage power fuse. And that's what they were using to protect power systems back, in the 1910s, 1911s. The problem with fuses is you're essentially one and done, right? And so the benefit of a circuit breaker, like the one in your house, as opposed to having fuses that if it blow, you have to go find the right size fuse and put it in, is circuit breakers can open and close many, 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 many times, right? So from a reliability standpoint, they're certainly superior to fuses. But we've been using circuit breakers now for, I don't know, maybe close to 100 years or so, but certainly for a long time. What are some of the opportunities for innovation in breaker design, given that, at the end of the day, that breaker really can only be in, three states: open, close, or transitioning between one of the two? What are some of the challenges driving the need for circuit breakers to evolve?
Yeah, you're exactly right, Dave. So circuit breakers have been around for a long time, and there are some tried and true designs. And as we've been looking at some circuit breakers, we've found that they could really benefit from some more modern material and manufacturing techniques, right? So moving a lot from casted parts to machine parts even is an opportunity.
What's wrong with the present ones?
There's nothing particularly wrong. They're just harder to build and more expensive to build, heavier. All right. So there's some opportunities along those lines for improvement. What I'm most interested in when we look at circuit breakers is really part reduction and simplification.
Okay.
So circuit breakers are really exquisite machines. They're very interesting mechanisms and very well designed. They're like a Swiss watch, right? But we know from SEL that the fewer moving parts, the better. That's why we have such great reliability. We're famous for not having moving parts. And that's pretty much all that a circuit breaker is a bunch of moving parts. So is there a way to reduce the complexity, reduce the part count, improve the reliability, and improve the performance of a circuit breaker? I think that's where opportunities for innovation lie. One example along those lines that I think is really interesting is instead of a mechanical spring to open up those contacts we were talking about, a magnetic actuator has like 90% fewer parts, and it actually moves faster. And so there's some things along those lines that I think could be pretty interesting for us.
And so we use magnetic actuators with, we don't build them, but we interface with them on our recloser control device, sends a signal up to a control at the top of the pole. It uses magnetic actuator. So we have used this technology before very successfully.
Right.
But let me ask you about the concept of these circuit breakers. Essentially, they're mechanical devices. Have we hit the fastest they can clear a device? We talked about the AC system. We're kind of in those systems, certainly at least the way we envision circuit breakers right now, we're really dependent on those zero crossings to clear the fault. So I may at the very top of that AC waveform say, hey, the circuit breaker should open up, and the contacts may open up, but until we hit that zero crossing, that there can be an arc, or one way or another current is going to flow until we hit that zero crossing. So we're kind of limited with the present way where circuit breakers are designed. We're limited by the laws of physics for how fast we can clear a fault. I bet you want to talk about our traveling wave technology, and it can detect a fault in, say, or a millisecond or two. And then we've got to wait probably for a good circuit breaker. There's like a 2-cycle, right? So that's 32 milliseconds. So we do it in 1 millisecond, then we wait around for 32 more milliseconds to clear a fault. Do you see any, I don't know, if we're looking forward, new technologies that can match where the circuit breaker can match the speed of the relay now?
Yeah, definitely. So I think current state of the art, I would say, is probably 2 to 3 cycles to clear a fault on a mechanical breaker, right? And I think it's important to ask, why is speed so important, right? Our relays are super fast, but who cares? And 2 to 3 cycles is pretty fast, right? But it's important to remember that these are overcurrent situations, short circuit situations, and bad stuff is happening, right? So you really want to clear that fault as quickly as possible to save equipment, to save lives, to be more efficient, to save energy. So that's why it's important to keep on pushing on speed in this situation. Waiting for a zero crossing is what really drives that 2 to 3 cycle limit. So we have to look at other ways, not waiting for a zero crossing, to make it faster. And as I was saying before, DC circuit breakers don't have that zero crossing. And so we already have to do things like use commutation circuits, maybe use hybrid or solid state devices in order to make that trip go faster, right? So a hybrid device will use a solid state commutation circuit to offload some of the energy while you open up the mechanical trip contacts. And that can get you down to about the low single-digit milliseconds for a clearing time. A true solid-state breaker can operate in 10 microseconds or so. And so that's really phenomenal, like orders of magnitude better than what we're seeing today.
So what you're talking about, is this aspirational or science fiction, or is it, no, this is certainly doable. You just got to want to do it.
Yeah, the technology has come a long way. Power electronics have come a long way in the last few years, but it is one of those things that's probably 10 to 20 years out for large circuit breakers. I think on the smaller end, we talk about the circuit breakers in your house and some of the industrial circuit breakers. There are possibilities to apply some of the existing technology today at those levels, kind of lower current levels.
So that's interesting though, right? Because we have high voltage DC systems, many volts, 1,000 kilovolt DC systems, I think is what they're putting up in China right now. So they know how to break and generate 1,000 kilovolts, right? A million volts. Why would we have to wait 20 years if this is what we really want to do? It seems like we got the technology either with SCRs or I think there's some new technologies coming in with transistors and stuff that we could start stacking those things and making some perhaps solid state circuit breakers.
Yeah, there are options and possibilities there. It's mostly an economical thing, right? And do you want to have a water-cooled circuit breaker? Do you want that complexity, right? Do you want the cost of implementing this and trying to get the heat out of these things? That's mostly the problem in solid state right now, and will continue to be for a while. And so if it's worth it, if the application is worth it and you want to spend the money, there are ways to mitigate some of those challenges. But I think for general commercial applications, it's going to take a little bit longer.
So here's something that got me really, you listed a number of reasons why you'd want to clear a fault as fast as you can. One, it just seems like the right thing to do. People have talked about power system stability. The faster you clear a fault, the more stable your system would be. There are a lot of calculations that go into how fast something has to clear, how fast protection should work versus other things, because you have to get into like scenarios of breaker failures and other things that, right, to calculate how fast you really need things to clear. But I start thinking about, well, let's just be a little bit pragmatic. If we can go fast, we probably should. Let's just assume that that's the right thing. And then I start thinking about how if we could clear really fast, how that impacts the design of, say, a circuit breaker. Mm-hmm. And here's an example, and it's, there's some corner cases where this doesn't work. But if we detect a fault, let's say using traveling wave within a millisecond, at that point, the machines that are pushing fault current, they don't even know it's really happened, right? So they haven't spun up, and at this point, there is no fault current, right? Mm-hmm. And if that's the case, then, are we really a circuit breaker or are we a circuit switcher, right? And the difference being that circuit switchers don't need to interrupt fault current. So I don't have to design, over design, if you will, the circuit switcher for those fault conditions, like I would have to design a circuit breaker for those fault conditions. So do we make the problem easier by saying, you know what, you don't need to interrupt 10 to the 1,000 amps. You just have to be able to interrupt load current at that point.
Yeah, that's a really good insight. The ratings on the breakers don't have to be as high if they can start operating earlier.
Yeah.
And they can clear the fault before that fault current really gets too high, right? So you can have a lower short circuit maximum interrupt rating on your breaker, which means it can be smaller. You don't have to use as many of maybe these hybrid or solid state components, right? Which makes them easier to cool, which makes them cheaper.
Yeah.
So it's really a system design problem at that point, right? It's like, how do we make sure that we're limiting the total short circuit fault current that can happen on this system?
We're going to get a bunch of hate mail or something like that saying that, oh, Dave, that's fanciful because you got to design the power system, with N-1 or N-2 contingency. So if that breaks, you still need something that can interrupt fault current back at the substation or wherever it might be. But I'd say I will concede that fact right now. So everybody doesn't need to send in a bunch of emails saying that's a goofy idea or some other words they might use to describe how crazy the idea is. But I think when we start thinking in these terms, right, they really open up new ideas. And if we start testing these things now, right, it'll allow us to perfect the technology, probably learn a lot, learn what works, what doesn't work. What did Edison say? It's not that I failed at building a fuse. What was the exact quote? I just know 99 different ways not to build one, right? So I think they're getting back into the lab and trying different ideas and seeing what works and what doesn't before we broadly deploy it on a power system, because it does like to remind us all the time that the power system isn't a lab. When we release something out there that's providing electricity to our homes or our factories, the stuff needs to be right. It needs to work all the time.
Yeah, that's exactly right.
Well, what else would you like to tell us about circuit breakers? Where are you guys at in your designs?
Yeah, we're pretty early on right now, but we're doing a lot of those kind of investigations like you talked about, right? Starting with a clean sheet of paper is a great opportunity to question kind of the status quo. Why is it this way? Why does it have to be this way? We're doing a lot of modeling and simulation. And so the ability to try a lot of different things, the crazy ideas and wild ideas, it's been really fun.
How far out are we from seeing it interrupt current for the first time?
Yeah, we should be doing that in the lab later this year at a scaled down level.
Well, I'm going to have you back then after the first interrupt, and let's see how the thing worked. If it's a pile of rubble or whether it's closed and opened multiple times.
That's right. I'm glad to do it.
All righty. Thanks, Kylan. Appreciate the time.
Thank you.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.